Right, Year 12, I'm just going to run through this worksheet which I've sent out to you, and where I basically run through the derivation of the photoelectric effect equation, which is the equation that Albert Einstein received the Nobel Prize for Physics for way back in the early 1900s. Okay, so it's a very, very famous, very important equation. Right, let's have a look at this. So you've seen the video on with me demonstrating the gold leaf electroscope. We've looked at the different observations and how they are evidence for the particle nature of light. So let's look at the equations now. Let's try and quantify these observations. Right. So the photon equation, which we've had from last lesson, was photon energy equals Planck constant times the frequency of the photon. Now this fits perfectly with our model of photons, where we can have red photons, we can have blue photons, we can have violet photons. All right. Now, so because they're self-contained packets of waves, we can actually they do have wavelength. Now, which one's going to have the highest frequency? The shortest wavelength is violet. So the wave is really bunched up like that. The ones with the longest wavelength are red light. So they're less bunched up. And then the blue one is somewhere in between, isn't it? Okay, so there you have it. So, and that fits perfectly with our idea that the E here, this is the individual photon energy in joules. Okay, and it's directly proportional to the frequency of the light within the photon. Now, if you remember, we have Planck constant, which is a very small value. So that is 6.6 times 10 to the minus 34, and the unit is the joule second. Okay, it's a tiny number. It's a tiny number because this energy is in joules. And this frequency is very, very high. You know, visible light is of the order of 10 to the 14. So to have a tiny amount of joules, we need a super tiny constant of proportionality. So there you have it. Right. Now, as you saw in the video, the photoelectric effect with the zinc plate, because I was using zinc here, the photoelectric effect does not occur, does not happen with visible light. It only happened when I use UV. And that's because UV has a higher frequency. If it has a higher frequency, it has enough energy in the photons to release the electrons. Okay, now just one really important thing here. For one electron to escape, it has to absorb the energy from one photon. Now, one thing about the photoelectric effect is the interaction between photons and electrons is always 1 to 1. That's absolutely crucial in understanding this. You can't have one electron absorbing 10 photons and then escaping. It doesn't work like that. Okay, it's a 1-to-1 interaction every time. So let's move on to this bit. The interaction is 1-to-1, like I just said. Right, that's the only way an electron can escape. Now, there's a really nice analogy I've come up with here, and that is the balls in a bucket analogy. Right, imagine you have a single zinc atom. Okay, you've got a single zinc atom. Now, the electrons orbiting the nucleus in a zinc atom can be likened, to balls in a bucket. Imagine you have a bucket full of tennis balls. All right. Now we can draw the bucket here. Okay. And inside this bucket, there are tennis balls. We're going to have tennis balls at the bottom. We're going to have tennis balls on top. And we're going to have another row of tennis balls. Right. In this model, the tennis balls represent the electrons. Okay. And to get out of the atom, to escape fully from the atom, the electrons have to get up to this energy level. They have to get up to this amount of energy, and then they can escape. This row of electrons obviously represents the electrons in the first orbital, the electrons closest to the nucleus. These are the electrons further away. Okay? Now, if we have an incoming photon, let's say it's visible light. Okay, here he comes. Now, we usually denote a photon by writing HF. Now, because it's visible light, that energy, that amount of energy, HF, is not high enough for this electron to escape, or any of these electrons to escape. Because for this row of electrons to escape, they have to overcome this amount of energy. Okay? Now, this amount of energy, the energy required for the outer electrons to fully escape, that amount of energy has a name, and that's called phi, or the work function. That is called the work function. Now, all metals, all different elements have different work functions. Now, zinc has a work function, which means that visible light is not enough. There's not enough energy in this photon to overcome the work function. Okay, so for zinc, we can say that, okay, for visible light, that the energy in the photon is less than the work function. That's why the photoelectric effect doesn't occur for visible light. Okay. However, for UV, it's a different story. For the UV, there is more than enough energy in the photon to overcome the work function. So that's what we see with our zinc plate. That's the explanation for what we observed with the gold leaf electroscope. Okay, that's the observation. That's the explanation for the observation. Okay, if we have a UV photon coming in, okay, now the amount of HF, the amount of energy in the UV photon is higher than the work function. So what does a single electron do? Okay, any ideas? Yep, you got it. There's a single electron can escape. That's why we see the gold leaf electroscope discharge. Okay, so there you have it. It's not just a really nice model there, really nice model. So let's think about this now. Because of conservation of energy, it leads us to a very, very, very important equation. It's Einstein's photoelectric equation. And this is it. Are you ready? Okay, the total energy in comes from what? The total energy in comes from the photon, doesn't it? So there you have it, the photon energy. Now that's equal to something plus the work function. Well, let's think about this. So for UV, because UV is high enough, that total amount of photon energy, some of it goes into overcoming the work function. So in this model, it would be like GPE, wouldn't it? Some of this goes to increasing the GPE of the electron. What's the remainder? What's the remainder? Any ideas? Well, you'd be right in thinking it's the kinetic energy of these electrons. These electrons get released with some kinetic energy, because there's more than enough in the photon for UV to overcome the work function, so they come flying out at some speed. So the missing term here is a half mv squared for those electrons. Just one last little thing, because the work function is for this row, it's not for this row, because that's more than the work function, and this row is considerably more than the work function to escape. The work function, this value for zinc, is just for the top layer. So if this electron gets emitted, it's going to have the most kinetic energy. If this one gets emitted, then it's going to have less kinetic energy, because it's had to overcome more of a jump to get out. And these ones, if they can be ejected, have to overcome a bigger gap, so they're going to have the least kinetic energy when they escape. So if it's the work function involved, it's this row, and then this half mv squared is a half mv max squared. So this equation here, if it includes the work function, then the kinetic energy is going to be the kinetic energy of the most energetic electrons, the fastest electrons that get emitted. Okay, so just to recap, let's write some things in. This is the total photon energy. Yeah, that's the total energy we start with. This is the kinetic energy of the fastest electrons, and this is the work function, okay, which is the energy for the outer electrons to escape. Okay, so there you have it. That's the Einstein's famous photoelectric equation. Obviously, it's an equation, it's got to be in standard units. So this amount of energy here is in joules. This amount of kinetic energy is in joules as well, and work function is in joules. They are quite often, though, quoted in electron volts as well, so just keep an eye on that. Just keep an eye on that. Obviously, if you wanted that to be in electron volts, then that could be in electron volts, and that could be in electron volts as well. That's fine. But obviously, if you want to go into calculating velocity, then you're going to have to get it into standard units. You're going to have to get this and this into joules. Right, there you have it. So there's a little intro to the photoelectric effect and its equation. What I want you to do is to have a look through these questions as well. I'm going to give you a few clues in the video where I demonstrate it with the gold leaf electroscope, but that's what I want you to have a think about next. Okay, well, there you have it. There's your task of the day, your second task of the day for this lesson. Have fun.